And so on this day, we're going to go through, again, a 35-minute tour of nomenclature. And so we're going to start kind of with the simplest things, and we're going to move to more complex things as we go. So we're starting with ionic compounds. And the reason we're starting with ionic compounds is, first of all, they make up the majority of compounds that we're going to deal with in this class. And second, they're the easiest to recognize. Ionic compounds, metal and non-metal. I've got metal and non-metal together in the same compound. I know it's going to be ionic. Now, at the beginning of this module, we were looking at the idea that atoms form ions, and that those ions that are made can either be positive or negative, depending upon the position of the metal on the periodic table or the non-metal on the periodic table. What we didn't get into a whole lot of at that time was the actual process. Now, a metal isn't going to just become positively charged for no good reason. The reason it would form a positively charged ion is because it's got some place for that electron to go. And so in the process of creating this compound, what we see is electronic transfer taking place. Metals giving their electrons to non-metals, and in the process, those metals become positively charged, those non-metals become negatively charged. Now, going back to where we were at this point last week, the charges that are made, we can predict off of the periodic table. The alkali metals are +1, the alkaline earths are +2, the halogens are -1, the nitrogen group is -3, and so on and so on. But the process that takes place is this electronic transfer process. The metals give their electrons to the non-metals. Now, as far as naming constructs are concerned, the naming that goes into this is also relatively simple. When we are talking about simple ionic compounds, and so we call these simple compounds binary, and we call them binary because they contain two elements. One element is a metal, the other element is a non-metal. For these binary compounds, the naming structure is simple. The metal gets named first, and it carries its full elemental name. The non-metal is named after, and its ending is changed to IDE. So oxygen becomes oxide, sulfur becomes sulfide, phosphorus becomes phosphide. And so when I put those two things together, I get compound names like sodium chloride, potassium chloride, sodium sulfide, sodium phosphide, calcium chloride. What we have to pick up on in this particular instance, however, is the chemical formula for these compounds does not match the compound's name in terms of multiplicity. There is no prefixing or suffixing here to indicate the number of ions that are present. And the reason for that is because the ions themselves are generated and are held by this concept of charge balance. And so what that means is, if we're looking at this from a standpoint of charge, I can recognize that the sodium has a +1 charge and the chlorine has a -1 charge. Those two charges match up, and anytime the charges in an ionic compound match up, we're going to be dealing with a 1-to-1 ratio of those two ions. But in these other cases, the sodium ion doesn't change in charge. It's always +1. But I notice that there are mismatches now in the charges based upon the other ions. The oxygen was -2, the sulfur was -2, the phosphorus is -3. And the sodium, with its +1 charge, has to adapt to those extra electrons that are being moved around. So in real simple terms, we can use the charges to dictate the formula using something called the crisscross method. And the crisscross method is simple. The value of the charge becomes the subscript for the other ion. It crosses from charge to subscript on the other, and the other one does the same thing. If the charge happens to be 1, then the subscript is going to be assumed. We don't need to write it. But otherwise, that charge turns into the subscript in every single one of those cases. And that's going to provide us the charge balance necessary to keep this ionic compound neutral and give us the correct ratio of elements to each other. So to match the -3 charge on the phosphide, we need 3 sodium ions because each sodium ion only has a +1 charge. So +1 times 3 gives us the +3 to match the -3 of the phosphide. So that's for binary compounds. Let's extend that just a little bit. Let's look at binary compounds that involve transition metals. One of the issues that we run into with transition metals is that a lot of times transition metals have charges. And not only do they have charges, they have multiple charges. And how do I know that I'm talking about copper 1 versus copper 2? Or manganese 2+ versus manganese 4+? The way that I distinguish a charge is through the use of Roman numerals. And so one of the easiest places to get messed up as a student, one of the easiest places to make mistakes is here, where instead of looking at that Roman numeral as the charge, a lot of students will accidentally mistake it for the subscript. And so a lot of iron 2 oxides on examinations end up being written as Fe2O because they're taking that Roman numeral and making it the subscript instead of making it the charge. Now, the key factor here, the thing that we really want to look at, is this idea right here. If I am given just the compound formula and not its name, I can determine its charge based on the other things that are in the compound. So that idea of crisscrossing, well, if I've got multiple subscripts, I can reverse the crossing and figure out the charges. In the case of something like FeO, what I have to rely on is the fact that I know that oxygen is -2. And since oxygen is -2, that must mean that the iron is +2, which is why we write this as iron 2 oxide. In this example, with the Fe2O3, I've got multiple subscripts here, so I can crisscross them back and recognize that, okay, the oxygen is -2, The iron is +3. This must be iron 3 oxide as a result. One little quick note here about mercury. Mercury does have two different forms, mercury 1 and mercury 2. Mercury 1 is a little bit of a trickster, though. You would think, based on its formula, that mercury 1 is just Hg+. However, this isn't the case. Mercury 1 actually bonds with itself to make a 2-ion molecule of Hg+. So the actual formula for mercury 1 is Hg2, 2 positive. Now, luckily for us, that's the only element that's really like that is that weird. All the other Roman numerals follow just normal charge kind of tendencies. So if I'm looking at tin 4, it's going to be SN4+. If I'm looking at cobalt 3, it's CO3+. There's nothing funny going on with any of the rest of them. One other important thing to note here. We've talked about the idea that there is variability in charges. Well, there are some transition metals that don't apply in that kind of way. So on the periodic table, we can draw a right triangle from aluminum down to indium, across to silver, and back to aluminum. This right triangle represents 6 elements who, even though they would be classified as transition metals, do not have multiple charges. These 6 have fixed charges. So silver only exists as a +1. Zinc only exists as a +2. And since that is the only form that it has, you will not see Roman numerals associated with those ions. Roman numerals are only there to help us differentiate between possible multiple forms of that ion. And in those cases, there is no multiple form. There's only one form, which is also why, for the alkali metals and the alkaline earths, we didn't write Roman numerals with those ones either. There's only one possible charge. We just write the name of the metal. We don't take it any further than that. The next place that we can take this is, what if we are looking at ionic compounds that are not binary? So examples of these would be ionic compounds that involve polyatomic ions. So one of the reasons why we had you go through that polyatomic ion proficiency and start working on those ions themselves is for this reason. Knowledge of these polyatomic ions makes a great amount of headway in terms of knowing how to name ionic compounds and knowing how to name acids. So we're not quite to acids yet, but that's coming. But structurally speaking, the structure for how we name polyatomic ion compounds is the same as what we did for the previous 2 ideas. It's the metal and the polyatomic ion. Or in the rare case where we use ammonium, ammonium takes the place of the metal. It is the only polyatomic ion on your list that was positively charged. Ammonium, and then whatever is attached to the ammonium. The crisscross rules still apply to polyatomic ions. We just have to be careful in their application. So let's take, for example, we have calcium acetate. Well, we know calcium to be Ca positive 2. From our polyatomic ions list, we know that acetate is C3 or C2H3O2 negative 1. The charges here don't match, so we're going to have to crisscross them to get the correct formula, which means the calcium is going to have a subscript of 1, so we're just going to leave it alone. And the acetate is going to have a subscript of 2. Now, how do I show a subscript of 2 on a compound or an ion that already has a bunch of subscripts? Here's where I have to use parentheses. So we're going to parenthesize the acetate ion, and that 2 that we were going to use comes out to the outside. So calcium acetate has the chemical formula Ca C2H2O2 taken twice. And so that taken twice or taken 3 times, that's how we indicate the parentheses applying to everything there in that ion, not just the oxygen or the hydrogen or the carbon, not individually. Structurally speaking, though, it's the same idea. Metal with charge when applicable, nonmetal or polyatomic ion as the second thing. Here, notice also, we just named the ion, we're not changing the ending to IDE. So that IDE suffix change only applies to the binary elements. So if I have fluorine or chlorine or oxygen or sulfur, that's where that IDE ending gets added on. Otherwise, if it's a polyatomic ion, it's been named as such for a reason. We're not going to mess with the ending of it. All right, let's do a couple of quick reviews. So first one here should be relatively quick. What is the name of FeO? All right, let's see how we did. Okay, we're a little bit split. Which one of these is correct? Because one of them is, and the other's not. Got to think about where iron is on the periodic table. It's a transition metal. And it's not in that right triangle of single charges, so it has to have a Roman numeral. Why is it iron 2? Well, we know that oxide is -2, so that means that the iron has to be +2 to give us that ratio. So C is correct there. All right, let's try another one. What is the name of KMnO4? All right, let's see how we did. All right, a little bit more scattered here. Okay, so right away, top two answers we should be able to eliminate. The fact that this is a non-binary compound means that IDE as a suffix is off the table. The only exception to that rule is with cyanide, because cyanide, Cn-, is a polyatomic ion that you can pair with other ions. And the only reason that cyanide doesn't have an ATE or ITE ending like all the other ones do is because there's no oxygen in it. All of the ATE and ITE polyatomic ions all had oxygen in them. The suffix ATE and ITE had to do with the number of oxygens. So the lack of oxygen means it's not an 8 and it's not an ite. It's an IDE, IDE. So A and B should be off the table immediately if we're thinking this through logically. Here we're talking about permanganate ion, MnO4. So potassium permanganate is correct. If you said potassium manganate, you're close. There's actually not a compound that's like that. There is no manganate ion. It's only permanganate. All right, a couple more things to look at and think about. We're not going to see these often, but I wanted to just give you an exposure to them. Ionic compounds sometimes can absorb water. And when they do so, and that water gets trapped in their crystals, those are called hydrates. And so the naming for hydrates just has to do with you take that ionic compound name and you add an additional sidecar on it, telling you how many waters are attached to it. And so the water is hydrates, and the prefix on it is the number of waters. Now, the prefixes here, you're going to see these prefixes again when we talk about covalent compounds. These prefixes are your geometric prefixes. So those prefixes are these. And again, you have seen these before in other places. So the prefixes here we're talking about are your geometric prefixes, the things that you use to name two-dimensional shapes: decagon, octagon, hexagon, pentagon. The only ones that are kind of different off of this, obviously there's no one-sided 3D object or 2D object, so mono is new. We use di instead of bi, and we use tetra instead of quad. But aside from those three differences, everything's the same. So you gotta go back to the recesses of your mind a little bit to find those prefixes that you used back in geometry back in high school. But it's there. You just gotta go back and find it. The other nice thing is that these prefixes come up again when we attach prefixes to molecular compounds. And we're going to do that right here. For molecular compounds, we are looking at compounds that involve two elements, and both of those elements are non-metallic. Two elements, both of the elements are non-metallic. They are made with a covalent bond. The naming for them is simple. Prefix, element number 1. Prefix, element number 2, IDE. Prefix, element, prefix, element I. So in a lot of ways, this resembles the binary ionic compound. The only difference is that with the binary ionic compound, we didn't need to use prefixes. And the reason we didn't need to use prefixes is because we had charges, and we could rely on the charges to tell us the ratio of the two elements. With covalent compounds, we don't have charges, so we have to use just prefixes to tell us how many of each element there are. So CO, carbon monoxide, SO2, sulfur dioxide. Now, why don't we put a mono in front of any of these? Well, it's an unwritten rule that if the first element only has one atom, we just assume it as one. So we don't need to write mono if there's only one of that first element. Why that doesn't apply to the second element, can't really tell you. I don't know. But for the first element, one is assumed unless otherwise told. All right, just a couple of minutes left here. Acids. Acids are very similar to what we've seen in these binary compounds. They look ionic because hydrogen's got a positive charge and the other thing would have a negative charge, but they're not ionic. They're actually molecular. Now, their naming falls into ionic-like kinds of tendencies. So for the binary acids, again, this is hydrogen with some other group of non-oxygenated elements. Usually it's just one. HCN, cyanide's kind of the exception here again. Hydrogen is listed first. The formula is hydro in front, the anion in the middle, and ic acid at the end. So basically, we're taking this. If we were looking at HF as an ionic compound, we would call it hydrogen fluoride. What we are doing to turn it into an acid is we are knocking off the gen and we're turning the ide into ic acid. Hydrofluoric acid. So we're taking that ionic structure and we're modifying it because acids are a little bit different. They're molecular compounds, but when we put them into water, they break apart like ions. So they're kind of both. That's why they're different. That's why we have a different naming system for them. In the outer world, they are molecular. Inside water, they act ionic. The other type of acid is the so-called oxoacid. Oxoacids are so named because they contain oxygen. And their naming system is purely based off of the polyatomic ion that they come from. If that polyatomic ion ends in ite, the ending of that ion gets changed to us acid. So the nitrite ion, for example, nitrite ion. Slap a hydrogen on there and it becomes HNO2. The nitrite gets turned into nitrous acid. Just a simple Little change at the end of the name. If the ion ends in ATE, so nitrate, NO3 negative. Slap a hydrogen on there, and we have HNO3. Nitrate gets turned into nitric acid. If there are prefixes on these ions, like per or hypo, those prefixes come along for the ride as well. So permanganate we just talked about, throw a hydrogen on there, and it's permanganic acid. Hypochlorite ion, OCl -1. Throw a hydrogen on that, and it becomes hypochlorous acid. The only thing that changes is the ending. We take the polyatomic ion ending, and we fix it to match acids. So I'm going to quickly open up two things for you here because I don't want you to miss out on participation points here. So we just did this one together. So it should be pretty easy to figure out which one of these is nitric acid, since I just gave you the formula for nitric acid. And so once you've answered that one, go ahead and answer this one as well. So both should be open at the same time here. And while you're doing that, let me just again remind you, this weekend, nothing related to nomenclature. We're just kind of opening the door there for you a little bit. Get ready for that quiz next week. That's really the only thing I've given you to do for the next 5 days. Have a great extended weekend. I'll see you on Wednesday.